Well, hello and welcome to 250, April 2nd, 2019. This is one of our later Zoom sessions in the course. Last week we finished off the topic of today's real ear, and we launch on into our latest unit, Fitting Methods or Hearing Aid Manufacturer Talks, Real Ear Walks. Hearing aid fitting software predicts, real ear proves. So, and last week, I will admit, it was kind of a raggedy-ass old Zoom session, wasn't that? I mean, all these retspools and suffice to say, and you're going, oh no, he's going back to it. Reference equivalent sound pressure level. All we're talking about with all that jazz is how do we get from dBHL to dBSPL. That was the whole question, because today's real ear takes you from the audiogram that you've entered into NOAA, and when you bink up a software, it's going to plot it in either dBHL or SPL, and I would urge you to plot your stuff in SPL as usually allowed by the software, because today's real ear is going to be followed up, and today's real ear plots everything in SPL. So real reference equivalent sound pressure level is just how do you get from the dial reading on your audiometer to the output from your headphone in a coupler. And insert headphones, 2cc coupler. Circumaural headphones, 6cc coupler. So you're going to have different retspools, RET-SPLs, for inserts than you will for circumaural, because the different couplers, different headphones, but they're consistent. They're built in, okay? They're built into your real ear equipment, because it's going to be X for inserts and it's going to be Y for circumaural, so those values don't change. And then you can add real ear to coupler difference, and you can take the average, and your machine will automatically do that. Your real ear equipment will automatically default to that, and it adds that to the reference equivalent sound pressure level, because RET-SPL gets you from the dial reading to the 2cc coupler, and real ear to coupler difference takes you from the 2cc coupler to the ear. Okay? And if you committed the sin of doing circumaural headphones, just add MAP at the bottom of the screen. Okay? Essentially that. Done. So enough on that. Now, let's look at today's stuff and look at hearing aid manufacturer fitting software talks and real ear measurements walk. And take a reading and an excerpt here. So I'll share screen, and we'll look at our notes. Here we go. Software talks, real ear measures walk. And this is an excerpt from my little book on page 158. And the article, there's an article in 2015, a great little article by Sanders, Studi, Weber, Mueller, okay? And it's called Manufacturers NAL 2 Fittings Fail Real Ear Verification. Hearing Review, 21-3, page 24. So here's an excerpt from my own text, and it says, another thing to note is that fitting software from different hearing aid manufacturers implements common fitting methods like NAL 2 and DSL 5 in different ways. And I put italics there because NAL 2 on Phonak is going to be slightly different from NAL 2 on Siemens, or I should say Signia, which is going to be different from NAL 2 on Bernafon. Okay, they each implement it differently, and you wonder why they do. I do know why they do. Okay, and we'll talk about that. Sanders, Studi, Weber, and Mueller 2015 looked at how various manufacturers implement the NAL 2 fitting method. Believe it or not, they do not all implement it in the same way. These investigators noted 4 things. They tend to give less amplification than the typical NAL 2 for soft inputs. They tend to give reduced amplification than NAL 2 for the high frequencies above 2000 hertz. They tend to give more amplification for the mid frequencies, and more linear gain than is prescribed for NAL2, by NAL2. So it's these things that they do. Let's paint the scene here. Say you have a client with some particular hearing loss. Hey Sam, how you doing? Let's say you have a client here with some particular hearing loss, and then you fit this client according to NAL2 that's available on the different software from each of the various manufacturers. On each software fitting, it says here, you would likely see resultant outputs that would come nice and close to the matching NAL2 targets on the software. It would look good. You'd be looking through rose-colored glasses. Not bad. But upon verification with real ear measures, however, you'd end up with different output results from each of the manufacturers, even though you used their NAL2 targets. Isn't that weird? This is why we cannot blindly trust manufacturers' first fit approximations. This is why we've got to verify predicted fitting methods with real ear measures. The only equipment that honest to goodness has NAL2 on it, as NAL2 intended, okay, is the real ear equipment. Whether it's Medrex, whether it's AudioScan, doesn't matter. The real ear equipment tends to have the accurate hearing aid fitting method. Now, why do people do this? Why would, I'll stop sharing for a second, why would a hearing aid manufacturer like Phonak or someone pay NAL2 thousands and thousands of dollars to be able to use their fitting method? Because they have to pay to use it. They can't just borrow it. You know, they got to pay to have it put on their software. So here's Phonak paying NAL2 umpteen $1,000 to use it. Then you're going to have Oticon doing the same thing, paying NAL2. So NAL2's making money hand over fist. And then you got Oticon using NAL2 differently than Phonak uses NAL2. Why would they bastardize the fitting method? Why would they change the fitting method? Why wouldn't they just leave it alone? And the reason they won't, and I wouldn't have known this a month ago, the only reason I know it now is because I met Gus Mueller at a conference in Victoria, British Columbia, Canada, early March, just before I went to Missouri Hearing Society conference. And I asked him the very same question. Why would manufacturers pay money to get NAL2 and then change NAL2 and not just leave it alone, unadulterated? And he said that's because they want to hit NAL2 targets easier. So then let's say Phonak will say, yep, now our hearing aids can fit NAL2 targets way better. Most audiologists are saying, yeah, Phonak's hitting NAL2 targets just great. Well, that's because maybe Phonak took NAL2 and bent it a little bit so that its hearing aids could fit the targets better. And there's no law against doing that. There's no clause in the NAL2 contract agreement saying you can't touch or change our fitting method at all. And it's the same with DSL. There's no shackles put on like a copyright saying you can't change this. When a manufacturer buys the rights to use the fitting method, they've bought the right to use that name. And they almost all taint the water somewhat to make you think that their particular hearing aids are able to hit NAL2 targets. But that's because they bent it a little bit. Weird, huh? I think that's really wild. This is something most people do not know. And so then the fitter will go, yeah, I tend to fit with Oticon, or I tend to fit with Phonak because I'm able to hit NAL2 targets with it, and I have a hard time hitting NAL2 targets with the other manufacturers, but I can do it with this one. So, but it's really because they did something funny. So back to our notes now. And Sam, before you got on here, I was kind of apologizing in a weird way because last week's Zoom session was a frickin' dog's breakfast. I mean, I was stumbling all over myself with these danged acronyms. I just about had a beer. I know I had a beer after that one. At any rate, you know what? At the very beginning of this Zoom session, I kind of encapsulated a little bit of what we were trying to knock out of the park last week. But anyway, all right, here we go. So let's share the screen here again. And so So we have this paragraph here. Let's paint the scene here. Say you have a client with some particular hearing loss. You fit the guy with NAL2 available by different manufacturers. On each software, you'll see resultant outputs that might look nice and close to matching NAL2. Upon verification with real ear measures, however, you'd end up with different outputs from each of the manufacturers. This is why we cannot blindly trust their first fit approximations. And I don't blame them for whatever they're doing, but it's not their job to do our fittings. It's their job to sell us hearing aids and to give us guidance in fitting their hearing aids. But it's our job to close the loop and finish the job. And that requires real ear. The picture's further complicated by the fact that manufacturers also provide their own proprietary fitting methods. And compared to the published fitting methods such as DSL-5 and NAL2, these methods tend to roll off highs even more. And this is likely done to reduce initial client discomfort, hearing aid feedback, and so on. But look above here at the 4 ways that manufacturers tend to taint their version of NAL2. They tend to give less amplification for soft inputs. They tend to give reduced amplification above 2000 hertz. They tend to provide more amplification for the mid frequencies, for loud inputs. And they tend to give a slightly more linear gain than NAL2. And in English, this just means they don't make the differences in gain for the different inputs as big. So they tend to give similar types of gain. Then if you take all these 4 into account, they're giving more similar gain for soft, average, and loud inputs, rather than having more different amounts of gain for soft versus average than versus loud. That's what I mean by more linear gain. So basically, working our way down the page, these guys found in 2015 that for soft inputs, the proprietary fitting methods ask for a lot less output, especially for the highs. For average inputs of 65, the proprietary fitting methods and NAL2 were actually quite similar, but the proprietary fitting methods still ask for less output in the highs. For louder inputs, the proprietary fitting methods provided even more output, especially for the mids. In general, proprietary fitting methods tend to most closely approximate the output required for inexperienced and new hearing aid wearers. Apparently, only real ear systems can be relied upon to truly stick to the fitting methods as they were originally designed. In our hearing healthcare field, real ear measurement is definitely considered as a clinical best practice by all these guys. Regarding the manufacturers, well, we really shouldn't point fingers of blame at them. Blame can be put anywhere, but the onus is on us to verify with real ear measurements. So just something to really consider. Now what we'll do is we'll go to our PowerPoint here and look kind of trail off from where we were last time, but here on the left would be a software's prediction of hitting targets. In reality, let's look at the middle one. And this is an actual true case out of Unitron. This is actually out of Unitron. Here was what the software, the picture the software painted. Here's the reality as seen by the same fitting method, NAL1. Okay, actually this was DSL4, I'm lying. Notice how the targets are right in the middle of the dynamic range. Okay, and look at how far shy of target you are at 4,000 hertz. Not 4, not 14, about 40. Here, you're painting it like really good. Now, maybe you don't want to hit the target here or the guy's going to wind up and punch you in the head. But the point is, this ain't that. Okay? That's the point here. DSL-5 child versus DSL-5 adult. Okay, we'll look at child version versus adult version for a sloping loss. Adult, child, or there's NAL1. Adult, NAL1 for 65 dB SPL inputs, average inputs. Notice how DSL goes a little further out in the highs. Now 1 tends to drop off. In fact, now 1 doesn't even talk about where the hearing loss is the worst. The targets end in thin air. Now 1 gives a little bit more in the middle. DSL gives a little bit less in the middle, but a little bit more in the highs. But basically, a man on a flying horse isn't going to recognize so much difference. Here's now 2. Now 1, now 2. I forgot to put a little hatch mark here for some reason. I don't know why, but now 2, now 1. So now 2 does give another target way out here. And notice how that's even below threshold. I guess they're assuming, well, some of this, if this mean here is touching this, then at least some of this will be at threshold, I suppose. But DSL-5 for adult for soft inputs, purple. Now 2 for soft inputs, purple. And again, this stuff here, remember, is just unaided speech. I didn't put a hearing aid on. I just had unaided speech coming out, the rainbow passage or whatever, when I just was looking at the targets. Of course, the job here for soft inputs would be to take this purple mean and have it cling on to these little plus signs, right? Have the mean here, the solid line, matching the targets. And would have this mean green match these targets, as shown here. There's the mean green, okay? So here's DSL-5 for adult. Now 2, now DSL-5 adult soft. Now 2 soft. And now look at the article by these 5 people, the article that we were talking about. Hearing aid manufacturers fitting softwares fail now, or fail real ear verification. So if you're looking at this, here we go. The red results for the manufacturer's proprietary fittings for male speech passage of AudioScan VeriFit 55 dB SPL input, soft inputs, averaged for 16 ears. Now 2 target is shown as a reference in red. So now 2 target for some mild to moderate loss, soft inputs, okay? And here's the manufacturer's proprietary fitting methods. Manufacturer's proprietary fitting methods compared to now 2 for soft inputs. Notice how they're all asking for less, with the exception of this green guy here, but then they're all asking for less in the highs. Next slide. Results for manufacturer's proprietary fittings again for male speech passage of AudioScan VeriFit with 65 average inputs. Average. Again, average for 16 years. Now 2 fitting shown as a reference. These are closer. They're closer. Okay? These were further away. This is better. Okay? But again, it's showing the proprietary fitting methods compared to now 2. Here's proprietary fitting methods compared to now 2 for loud inputs of 75. Okay? So look at what they're doing. This is what I meant by, in a way, they're more linear. Okay? Because you'd think with loud inputs, they'd be offering less. But it's as if they're keeping the amount of gain and output quite similar for average versus loud. Because look at the proprietary fitting methods, they're asking for more than now 2 for loud inputs, especially in the mids. Weird, huh? Average, soft. Okay, so for soft, they're underfitting. For average, they're quite close, but still all less in the highs. Okay, that's one thing. Manufacturers' proprietary fitting methods always roll off the highs. Okay, but they're doing a better job here at 65 than they were at 55. But remember, this is compared to now 2. Okay, and then for loud inputs of 75, they exceed now targets, especially for the mid frequencies. And they seem to be at or near now targets for the highs here, but more for the mids. So now we're going to look at and read this. It's a busy slide because from here we'll look at A, B, and see closer, okay? But this is just a description of all three of those together. Read what it says in the white writing here. And this is all from that one article. Sanders, Studi, Weber, and Mueller, Hearing Review 2015. At figure A, 3A to C. The average difference values for the real ear output of the manufacturer's NAL2 compared to the NAL2 targets on the AudioScan real ear system. Okay, so now we're looking at how do the manufacturers use NAL2 compared to how does the real ear systems use NAL2. Always make sure we're following ourselves here, okay, because this slide, these three slides are talking about how the manufacturer's proprietary fitting methods compare to NAL2 for the different inputs. Okay, here we're looking at how does each manufacturer's implementation or version of NAL2, how does their NAL2 differ from the from NAL2 found on real ear systems? That's what the point is here. Read again. Average differences for real ear output of manufacturer's NAL2 compared to NAL2 on a real ear system, derived using the male speech passage again for 55, 65, and 75 dB SPL inputs for panels A through C respectively, 55, 65, 75. The zero line, follow my cursor, the zero line indicates or represents prescribed NAL2 values. Now, please don't think it's talking flat gain. It's just saying call the zero line whatever NAL was doing, okay? And then points above the zero line indicate something, a NAL2 output on a hearing aid manufacturer that's more than what NAL2 would be on a real ear system. And anytime you're below the zero line, it's showing you how the manufacturer's version of NAL2 is less than the NAL2 on real ear systems. Okay, so let's look at A first. Read it again. Here's read the writing again. Average differences for manufacturer's NAL compared to NAL on real ear. Derived using, and here I'm calling it 55. I've made it larger there, okay, because that's what this one's talking about. This A is here. So we're looking at it close up. The zero line represents whatever NAL said. And again, please don't think that it's saying a flat amount of output. That's not what the issue is. The zero line is just, say NAL2 asked for outputs called X. Whatever they were, for some sloping, mild to moderate, sensory neural loss, what did NAL2 prescribe? X, okay? X amplification at 250, X amplification at 500, whatever it was. So whatever so here's the green. Look at the green. Hearing aid manufacturer 1, hearing aid manufacturer 2, 3, 4, and 5. So let's look at red and green. Manufacturer 5 was really about the closest. It asked for a tad more than NAL2 here, a bit less than NAL2 here, the same as NAL here, a little bit more than NAL here, the same as NAL here, a little bit less, and a little bit more or less in the highs. Hearing aid manufacturer green asked for very close to NAL targets for the low frequencies below 1,000 hertz. But as soon as you got above 1,000 hertz, the manufacturer's version of NAL2 asked for a lot less high frequency amplification than the NAL2 would be that is found on the real ear system. So we'll make sure we're quite clear here. Let's say Ted walked into your clinic and Ted came out from a hearing test, and I had a mild to moderate sloping loss, typical sensory neural hearing loss. You fit me according to NAL2, okay? And you fit me according to NAL2 on Phonak. And then you fit me according to NAL2 on Unitron software. And then you went to Oticon software and you picked out NAL2 and you fit me according to that. And then you went to Bernafon software and you looked for NAL2, you binked in my hearing loss and you fit me according to their NAL2. And then you went to Starkey and you binked my audiogram into Starkey software and you chose NAL2 on Starkey software and you fit me that way. So now I've been fit with 5 different hearing aids, all of them according to NAL2 on Starkey, NAL2 on Bernafon, NAL2 on Oticon, NAL2 on Unitron, NAL2 on Phonak. Then you brought me over to the Real Ear system, and you found out what happened. So you binked in my audiogram into the Real Ear system. Then you chose NAL2, and you looked at my targets, and then you took the Starkey, you did Real Ear on me with the Starkey hearing aid. Okay, let's say for example, and when you did Real Ear with me, and the hearing aid's programmed according to Starkey's version of NAL2, identical audiogram, you might have found the green line. You might have found, yep, you were pretty close to the NAL targets as seen on the Real Ear software, but you were shy of NAL targets on Real Ear. You were meeting NAL targets on Starkey software, but you were short of NAL2 targets as seen on the Real Ear equipment. Okay, because the Real Ear equipment isn't grabbing Starkey's version of NAL2 and putting it in. The Real Ear has its own version of NAL2. So then you took off the hearing aid and you put the Oticon hearing aid on. And we'll call it the red. For example, I don't know which ones these are. They're all hidden. It's a blind study. They're not telling us who it is. But with the Oticon hearing aid programmed according to Oticon's NAL2, and you'll find out it's fairly similar to the Real Ear system's version of NAL2, but I'm shy of targets there too. Not quite as bad as I was with Starkey, but still shy in the highs. Then you took that hearing aid off and you put on Bernafon's hearing aid, programmed to the same hearing loss, according to Bernafon's NAL2. Then you did put the probe tube in my ear, and you did Real Ear, and you find out the black line. Whoa, I was way shy. I was close to NAL2 targets on the Real Ear system. I was close to the Real Ear's version of NAL2 in the mids. Fairly, still shy, but how much was I shy? Well, this is -5. So I was about 3 shy of target. And then in the high frequencies, whoa, I was about 15 decibels below target. So, maybe Bernafon's version of NAL2 differed from the Real Ear system's version of NAL2 by some 15 decibels in the highs and by some 10 decibels in the lows. You get it? So that's what the point is. The 0 line represents the prescribed NAL2 values, whatever they were. And then these various colors here, how they vary around the 0 line, shows you how their NAL2 versions differed from the Real Ear version of NAL2. And you can see that almost never were they more than NAL2. The Real Ear, I should say the manufacturer's version of NAL2, almost always gave less than the original unbastardized NAL2 found on the Real Ear equipment. That's the point here, okay? And that's all for 55 decibel inputs. Let's look at 65. Now you're at 65. Again, the 0 indicates what NAL was doing. Whatever it was doing, we'll just call it X, or now we'll call it Y. Okay? And here you can find that 2 of the manufacturers are actually giving more than NAL2. So their version of NAL2 with average inputs was giving more than the Real Ear version of NAL2 for average inputs in the lows. And in the highs, once again, they're below, especially the green. And then the other ones, the black, the blue, and the purple, they're all kind of still below. Their versions of NAL 2 are all still below the version of NAL 2 on the real ear system. Okay? But here you got a little bit that's doing more. Now let's look at 75 dB SPL inputs. Now for 75, watch what's happening here. Lots of them are asking for more. So the version of NAL 2 found on Phonak, found on Oticon, found on Starkey, found on whatever, on 5 different manufacturers, versions of NAL 2 for loud inputs of 75 dB SPL, those are prescribing more output in the mids frequencies than the NAL 2 on the real ear system. And they're all asking for less than NAL in the highs. See that? So that's kind of what we meant when we talked about this. Up, up. Okay? Less amplification for soft, reduced amplification for highs all the time, more amplification for the mid frequencies for loud inputs. And so basically, the gain is more linear. Okay? They're asking for more similar amounts of gain for soft versus average versus loud. Tends to be a strange thing. So these points here are reflected in if I can find it, okay, are reflected here and here and here. It's a very important article. It's an article that I would Google up if I were you and have it at your fingertips, because this doesn't cement the reason why people should do real ear. I don't know what will. This is really it. This is kind of the center of the universe that way. This shocked me. I had no idea. I did not know that. I thought that manufacturers' fitting software had to use the original fitting methods, and they don't. They buy the rights to the titles, and then they taint the waters, each in their own way. And usually they roll off the highs. Even with their versions of NAL 2, they roll off the highs. Not as much as their proprietary fitting methods. The proprietary fitting methods really roll off the highs. But even the manufacturer's versions of NAL 2, they tend to roll off the highs. Why? So it'll look like you've got a better fitting. And you'll think, yeah, I'm fitting with NAL 2. They're never going to tell you they're not. Okay? So it's an interesting thing. But again, let's save our disgust against the manufacturers for doing this. I would just leave it neutral and just kind of tip my hat and say thank you for giving us your software so that we can get ourselves into the ballpark. Appreciate it, because couldn't fit your hearing aid without your software. But I'm not asking you, Mr. or Mrs. Manufacturer, to do my fittings. I'm asking you to sell me your hearing aids so I can sell them to the end user. So if you sold me the hearing aids with your software, and I'm using it, you've given it to me, it's on NOAA, it's all part of it, can't fit your hearing aids without it, but I have to finish my job, and I am the clinician. And I finish the job by verifying with Real Ear so that I can look at the Real Ear's version of NAL 2 and really do the job. It's really, I think this is one of the better articles, especially for emerging students, to take a look at really carefully and read it. It's a great article. It's so software talks, Real Ear measurement walks. Totally different situations. If we go now to what we saw here on our notes, we'll scroll down the page and look at a little bit of open fit and RIC hearing aids, receiver in canal hearing aids. Oticon sometimes calls its receiver in canal hearing aids, they call them RITEs, receiver in the ear. Okay, but Ricks, Wrights, open fits, all of them, you can fit them with very wide open dome ear molds. Okay, wide open vented stock ear molds, especially the ones with lots of holes in them, hence open fit. We all realize that they don't have to be completely wide open. We all realize that the domes, of course, can be smaller and smaller. I'm going to look in my little bag of goodies here, and just, you've seen this before, but why not? We got the time. So I'll just stop sharing for a second here. So you're looking at a dome here with lots of holes in it. Okay, that's going to be about a 4 millimeter vent. I mean, taking all those holes into account. All right, so this is what you would call an open fit hearing aid. That's kind of what the issue is on this bottom part of the page. These can present problems when doing real ear. Open fit BTEs became popular around 10 years ago. Ricks became popular a few years later. Really make sure we realize that we have a concrete reality of the difference between a Rick hearing aid and basically an open fit hearing aid. Just want to make sure I've got it here. I'm pulling out my little bag of hearing aids. There we go. I'll put a little dome on this one here so it looks okay as well. There it is. That's the one I wanted to show you. Okay, stop sharing. Be sure, O class of OTC, look at these two hearing aids. Quite similar. Both of them open fit. Okay. There we go. Turn this guy so you can see they're both open fit hearing aids. Okay. This one's a Rick because it's got a wire. Woo. Where am I? There, it's got a wire running through the tube, and the receiver is in the canal. The receiver is in the canal. Okay, that's the receiver, and of course the dome on the receiver. Thin tube, the tube itself is hollow. No wire through it, only sound. The receiver is inside the hearing aid. Sound is traveling through here, whereas of course with the Rick hearing aid, sound is not going through the cord. Okay, electricity is going through the cord, and that electricity is being changed by the receiver into sound. Just harking on an old thing that we should have known from last year, but just making sure we've got it straight. And besides, it wastes a few more minutes on a Zoom session. So here we go. Share a screen once again, go to our notes. Open vent is a two-way street. Sound can travel in and out of an open vent. You also need more gain to compensate for the loss of frequencies below 1,000 hertz. Thin tube effect for open fit BTEs. You've got a thinner tube, so that's for the thin tube I showed you, okay, not for the Rick, but for the thin tube. The smaller diameter of tube, of course, is going to affect the highs. Look, if I stop sharing, and we'll look at a thin tube, and we'll look at a number 13, here's a 13, number 13, and here's a thin tube. Look at the difference in the diameter of the tubes. A number 13 tubing has 2 millimeter diameter. Thin tube has less than 1 millimeter diameter. What happens when I talk into a piece of paper like a horn, and I'm talking to the small end, and the sound's going out of the wide end, you can hear the high frequencies of my voice. If I'm talking into the wide end, you can hear my voice is more muffled. Okay? So a thinner tube tends to cut out the highs. So thin tube BTEs had to overcome that and have their amplifiers really pump out the highs to compensate for the loss that you're getting through that little thin tube. So there's two things to note with the tiny little BTEs like this. Okay? Whether if it's a thin tube, you often have an open vent, And you can choose a dome with fewer holes in it. It doesn't have to be the great big honker holes, okay? You can choose tulip vents and whatever the kind that have smaller holes in them. But the point is the thin tube itself can really knock out the highs, okay? With a RIC hearing aid, you're not worried about that thin tube because no sound is going through there anyway. Sound is just going to the receiver that's hidden beneath the dome. However, you still, if it's got a wide open vent, that's going to affect what happens in the frequency response of the hearing aid. Thin tube effect for open fit BTEs. So let's just see if I've got a picture of that in our good old notes. You'll notice I'm skipping slides now in the PowerPoint. I'm jumping from slide 15, and I'm going way down. Let's see where we go. All the way down. I'm jumping down to number 45. Okay, I'm just jumping all the way down there. I'm just skipping because next week we're going to look at the slides in between. Okay, but not right now. Next week we will. So here we go. We're looking at verification with thin tube BTEs. Here's 0 dBHL, or minimal audible pressure. Here's someone's hearing loss. Here's frequency-specific loudness discomfort levels. And they say when you're running with a thin tube and a wide open vent, you should equalize the sound field with the hearing aid turned off or muted. Repeat if the client or nearby objects remove or move. Push this button to make that happen, and then after equalizing, turn on the hearing aid and run the test. Well, what they're trying to do there, and every manufacturer's real ear system is going to handle this a little bit different, but what they're talking about, thin tube open fit BTEs, recall the job of the reference mic, the little thing I'm pointing to right there with my arrow, is to make sure, look, is to make sure, nice spelling, Ted, is to make sure that the sound level at the ear is constant. Okay, so if you've got 65 indicated, the speakers had better be emitting 65, and the reference mic is going to make sure that they're doing so. Chances are on your real ear system, if you moved your head closer to the speaker, the sound from the speaker would get softer. If you moved your head further away, the sound from the speaker would get louder in order to maintain 65 dB SPL being picked up by the reference mic. But sound coming through the vent will also be picked up by the reference mic. Okay, so sound leaking out of your big vented hearing aid here will also get picked up by the mic. So basically, if you're looking at thin tube open fit BTEs, the vent is a two-way street. Sound can go in through the vent, like natural sound can enter, but vents also allow the lows to escape, right? The occlusion effect, that's what they're doing. So you can see your vent loss taking place below 1,000 hertz, as it should, but also look at the thin tube effect of thin tube BTEs. Remember, with regular tubing, you might have this frequency response, number 13 tubing, 2 millimeters diameter. Thin tube, less than 1 millimeter diameter, you're going to cut off your highs. That's the demo I was showing you with the horn there. Amplified sound and vent interaction. So let's jump back 2 slides. Here's your vent. It's letting out the lows. But see how vents allow sound coming in as well as coming out. And the sound leaking out of the vent to get rid of the occlusion effect might interact with sound coming into the vent naturally from the outside, and you'll get what you call a comb filter effect, kind of like the teeth of a comb. In phase, out of phase, in phase, out of phase. So you're going to get some strange things that can happen. Open fit can give a pleasing mixture of in and out sounds, but beware of the comb filter effect. And this is not so much, or this can be, you know, if you've got wide open vents. This is what one possible concern is. But when you're doing real ear, Remember we were saying earlier that sound can leak out of your big vent and also get picked up by the reference mic. So watch what happens here. Due to large vent, sound escapes and contaminates the inputs. The reference mic measures an increase in SPL, so the real ear system reduces its speaker level because it's getting sound that's leaking out of the vent. So to keep things at 65, the speaker is going to get a little softer. It's getting a little extra help with the sound leaking out. So here might be your true response, but it's going to end up in an underestimated hearing aid output because the sound from the speaker is being reduced. So you're going to crank it up to make it work. Okay? And you're going to crank up your hearing aid's gain and output, and it's going to lead to over-amplification. See? So once again, same here. Reference mic may pick up increase in SPL. The real ear system thus reduces your test stimulus level coming out of its speakers. So now here's might be your true response, but here's now your contaminated response. You want this to be here, so you're going to increase your hearing aid's gain and output, and you're going to result in overfitting. I'll finish with this. These are just a couple of cautions. And by the way, what should you do about that? Not a lot. You know what you can do? Your real ear systems allow various ways to get around it. The one way I talked about was using that equalized response. By turning off your hearing aid and then allowing the room to be balanced or whatever with the sound leaking out of the hearing aid. So now you can turn on the hearing aid and your system will subtract that crap that it measured while your hearing aid was off. And that's what I meant by this slide right here where I talked about, hang on here. Okay, where we talked about, here, this equalizing business. Equalize the sound field with the hearing aid turned off. That way your system's picking up whatever sound might be leaking out. Okay, or it might, so you got the person just sitting there. Now you're turning the hearing aid on, okay, and your system will fix things by not including, and I don't know exactly how that all works. Every system does it differently. Verifit often does it this way, but I'll show you a simple way to really do things without even messing with any of the stuff here. Make the blue looping a little longer so the box hangs down a little further. Just a centimeter lower. So you make this loop a little bit longer. And when you've done that, the reference mic is further away. And you know what? You'll barely pick up any sound leaking out of that vent. So there's various different methods. The Oracle system by GM Resound or whatever, Great Northern, they have a different way of getting rid of this leaking out of the vent business with open fit VTEs. But so just be aware that that does exist with open vents. That leaking sound can contaminate what's coming out of the speaker of the real ear system. That's basically was the point of all this. So now let's look at the study done with thin tube open fit VTE some years ago to compare software predictions to real ear proof. 14 hearing aids from 9 manufacturers. Client experience level was set to maximum. Hearing aids were set to either Now 1 or DSL-4. You recall DSL-4 was the powerhouse precursor to DSL-5, okay? So anyway, the feedback manager was run only if recommended by the manufacturer. Here goes. You had 2 groups of clients. One had minimal hearing loss on an average. One had more hearing loss on an average. And these little dots, all they are is showing you unaided speech in dBHL. And there's exactly 100 dots there. And each dot represents 1% of the cues necessary in order to understand what was said. And you'll notice most of the dots are hovering around between 1 and 4,000 hertz, just saying that most of the cues for understanding what someone said are basically in the highs. But ignore that. Here you've got your mild hearing loss and your little bit more mild to moderate loss. So here's your NAL1 targets for this hearing loss, the mild loss. And look at the variation. The NAL1 target match, minimum hearing loss. And look at how much all the manufacturers varied around it. But all of them were asking for less in the highs. DSL4 target match. Now DSL asks for a lot more than NAL. See this? Look at DSL4 targets for the mild loss. Way up there. So the manufacturer's versions of DSL4, and look at how they're varying all over the place, but all of them less in the highs. For the maximum loss, for the bigger loss, now we're looking at this hearing loss here. And we're looking at the NAL1 targets for that loss. And almost all the manufacturers less. DSL4, don't even try. Because all of the manufacturers' versions are asking for well below what the real ear version was. Look at the proprietary fitting methods now. Not looking at the manufacturer's versions of NAL and versions of DSL4, but now the proprietary fitting methods. Here's the DSL for the minimum loss. So look at the blue and the red. Those are the targets for DSL4 and NAL1 for this loss. Okay? And look at how the proprietary fitting methods are all well below both of those, especially in the highs. When we look more at the more moderate loss, of course, your targets go up. So the more moderate loss, of course, is this one shown here. And you're looking at the NAL1 and the DSL4 targets for the more maximum loss. And the manufacturer's high frequency, here's the proprietary fitting methods compared to these two fitting method targets for that bigger hearing loss. And the proprietary fitting methods are all less. Okay, so this is just, again, underlining the fact. Manufacturers buy the rights to these methods, but they also alter these to suit their needs. Manufacturers also have proprietary fitting methods. These tend to roll off the highs, and I would say even more than the manufacturer's versions of NAL and the manufacturer's versions of DSL. Those roll off the highs as well, but the proprietary fitting methods especially. Software, bottom line here, almost always overestimates the gain and output from hearing aid. Real ear almost always shows less than predicted. And you know why? It's really because manufacturer software also, let's forgive them a little bit, they are using artificial intelligence. They're taking the hearing loss, the fitting method, the mic location effect, the real ear to coupler difference, the reference equivalent sound pressure, all these things they're taking, okay? And they're adding them together like this, plus this, plus this, plus this, plus this. And they're coming up with their target. Whereas when you're measuring with real ear, all those things are happening together in real time. Okay? So prediction is saying this plus this plus this should equal this. Real ear, everything is acting together in real time. That's another reason why real ear tends to differ from manufacturers' fitting targets. But the other reason is a little more sinister. Manufacturers' proprietary fitting methods always ask for less, especially in the highs. And manufacturers' versions of NAL2 and DSL5 also, and NAL1 and DSL4 also almost always ask for less, especially for the soft inputs and always for the high frequencies. Let's see where we could have gone here in our PowerPoint slides, because we're just about all done. There you go, we are done. Okay, so I will take this, we'll look at our handwriting here again, move on up the page, and look at these 4 points. Okay, tie those 4 points, especially the top 3, especially these. Look at those 3. And tie those, a big bunny knot between those sentences and this slide, this slide, and this slide, and this slide, this one, and this one. Look at these slides very carefully, okay? Because looking at slide, and I'll just make numerical indications of these. Slide 8 is talking about 5 different hearing aid companies and looking at their proprietary fittings versus NAL2 for some imaginary hearing loss. Okay, proprietary fitting methods for soft inputs of 55, proprietary fitting method targets for 65 dB SPL inputs, proprietary fitting method targets for loud inputs of 75. And look at how they all differ from the red line of NAL2. Okay, 55, 65, 75. Note the trends. Very important to carry this in your back pocket. Then you're going to the next series of slides here. And this is talking not about their proprietary fitting methods. No, this is talking about how their version of NAL2 differs from the real ear version of NAL2. And once again, you're looking at 5 different hearing aids, the same 5 different companies. So very important article summarizing in a better way than I ever could on my own what happens in today's hearing aid fittings and how utterly foolish it is to walk completely in the shadow of hearing aid manufacturers, letting them wave the baton and you just singing along. Best to really take control and follow up their fitting and do real ear and see it for yourself. Only then have you finished the fitting. Okay, now we're done today. What we'll do next week is we're going to look at case examples of how past students of mine in projects have programmed hearing aids to real ear and what they found to be the differences. So we'll look at some case studies here, okay? For now, adios amigos. We'll see you when we look at you. I'll stop recording now.